video we're going to get into graphing logs. So since we know that exponential and log functions are inverses, we can switch the coordinates of the original function or the exponential to get the points of the inverse function or the log. But this is actually really important because like for an exponential function, the domain was all real numbers. We'd write that in interval notation like this. But for a log function, that's actually the range. And for that exponential function, the range was all these y values that were greater than 0. That becomes the domain of the log function. It's the x values that are all greater than 0. And we put parentheses here because we can't include 0 since it has this vertical asymptote at x equals 0. It's never going to hit that x value. So the equation for the vertical asymptote is x equals 0. And actually, if you look at the graph, it's always increasing from left to right. So I'm going to write that as always increasing. That means it's never decreasing. And I'm going to write none for a horizontal asymptote because a log graph doesn't have any kind of horizontal asymptote. I know it looks kind of like it's leveling off here, but it does keep increasing forever. It's going to go up and hit every single y value. Now, when you're actually graphing a log function by hand, there's a couple steps involved. And if you follow these steps, it should work pretty well for you every time. It tells us step 1 is to find the vertical asymptote, and we do that by finding the solution to x minus c equals 0. That just means we're going to take this inside thing and set it equal to 0. If we did that, we would add c to both sides, and then we would get x equals c. Like, remember, if this said x minus 3, we would think of a transformation as moving that right 3. So the vertical asymptote would be at x equals 3. Graphing the vertical asymptote right away just helps us get kind of a bearing of where the graph is going to be located. The next part is kind of tricky. It says to rewrite it as an exponential function. And it says in order to do this, you have to isolate the log term first. So we're going to move the d value first by subtracting or adding it or whatever. In this case, I'm going to write minus d. And then divide both sides by a. And now that you have the log term isolated, you can do around the world to rewrite it in exponential form. So in order to do around the world, you start at the base, which in this case is b. So b to the other side of the equation, and then you go back to the inside of the log. So that's telling me to start with b, and then write to the y minus d over a power, which is pretty obnoxious. In practice, it isn't usually that bad. But then we go back into the inside of the log, so equals x minus c. And we're really close. We might as well just get x by itself by adding c to both sides. And this is all one term here, so I'm going to write b to the y minus d over a power plus c equals x. So this is like worst case scenario if you had like every single transformation that you'd have to deal with. Again, in practice it won't be that bad, but now that we have it in exponential form, it says plug in values for y, not x. The reason for that is because in log form, most of the x values you'd pick to plug in wouldn't work very well. But in exponential form, you can plug in any y value you want, and raising something to any power isn't too bad. It's pretty easy to do on a calculator. So you'll just make an xy table, pick a couple y values, plug them in, get x values, and then plot them. So let's take a look at the graph of this function, log base 3 of x plus 2. I know that the plus 2 inside the function is going to move it left 2. So that means the vertical asymptote is going to be at x equals negative 2. And there isn't any horizontal reflection inside the function, so I know this thing's going to be branching off to the right. So the domain is all the x values that are greater than negative 2. To get the x-intercept, I'm trying to find the x value that I would get if I had a y value of 0. So I'm just going to set this equation equal to 0. And the log term is already isolated, so I'm just going to do around the world. So 3 to the 0 power equals x plus 2. And anything to the 0 power is 1. So 1 equals x plus 2. And if I subtract 2 from both sides, negative 1 equals x. So the x-intercept is at negative 1, 0. The y-intercept is whatever you get for the y value when you plug 0 in for x. So that would be log base 3 of 0 plus 2, which is log base 3 of 2. And remember, if you think about like around the world, this is saying 3 to what power equals 2? 3 to what power equals 2? And that's not immediately obvious. So you're going to have to type that into your calculator. And if your calculator can't do logs with different bases, you would just use change of base formula. So this would be log of 2 over log of 3. And then this is the common log, which most calculators can do. In this case, it's 0.6. In this case, you get roughly 0.6. So I'm going to start by just plotting this much. And the last thing there is to do is just get a couple more points by making an xy table. And I'm actually going to start by putting this in exponential form. So this is going to feel a lot like what we just did. I'm going to do around the world, so 3 to the y power equals x plus 2. And then subtract 2 from both sides, so 3 to the y power minus 2 equals x. Now I can make an xy table. And I already have these points here, so I'm going to pick two different y values that I don't have yet, so maybe like -1 and +1. So if I plug -1 into this, 3 to the -1 power is 1/3, and 1/3 minus 2 is -1 2/3. If I plugged 1 in, I'd have 3 to the first power, which is 3, minus 2 is 1. So now I have these points -1 2/3, which is really close to -2, comma -1, so like right here, and then 1, 1, which is over here. So you can see the graph, again, is approaching this vertical asymptote of x equals -2, and then kind of sloping off to the right. The next example is very similar, but the +2 is on the outside now. And that's just going to shift the whole graph up 2. But since it hasn't been moved left or right at all, the vertical asymptote is going to be x equals 0, and the domain is all the x values that are greater than 0. Remember, something like log base 3 of x is saying like 3 to what power equals x. And so it only makes sense for this to be a positive number, because 3 to some power can only be a positive number. So knowing that the vertical asymptote is x equals 0, and that we're only going to have positive x values, you know you're not going to have a y-intercept because this thing can't cross the y-axis. So you can just write none. It will have an x-intercept somewhere though, because the range is all real numbers. So I know the x-intercept is going to be some point on the x-axis where the y value is 0. I'm actually going to hold off finding that until just a second when I have this thing in exponential form. So let's rewrite this as y equals log base 3 of x plus 2. So I have to isolate the log term first by subtracting 2 from both sides. So I have y minus 2 equals the log base 3 of x. And now I can do around the world by starting at the base 3, going around the equal sign, and then back inside the log. So this would be 3, and then to the other side, so y minus 2 equals x. And now x is already alone, so I can just jump right to making this xy table, and then plugging in some y values. I wanted to know what x equals when y was 0, so I'll definitely put that in there. And then maybe just a couple more like -2 and +2. So if I plugged in -2, that would be 3 to the -2 minus 2. Alright, so -2 minus 2 is -4, and 3 to the -4 power is like 1 over 3 to the 4th power, which is a really small number. It's like 1 over 81. The point is basically 0, so like incredibly close to 0 at -2. Basically on the y-axis, just not quite. Alright, if I plugged in 0, that would be 3 to the 0 minus 2, and 3 to the -2 is like 1 over 9, so still a really, really small number. And finally, 3 to the 2 minus 2 would be like 3 to the 0 power, and that's 1. So this function starts out by hugging this vertical asymptote x equals 0, and then branching off to the right. This last function has quite a few transformations for us to deal with, so before we worry about filling out any of this information, let's just rewrite this in exponential form first. So the first thing I'm going to do is get rid of this -4 by adding 4 to both sides, and then I'll have to get rid of the 2 by dividing both sides by 2. Now that I finally have the log term isolated, I'm going to start at the base and do around the world, so 4 to this other side equals this. So 4 to this power, which is pretty obnoxious, y plus 4 over 2 equals the other side, so x plus 1. And I might as well just get x alone by subtracting 1 from both sides. And this is all one term here, so it's going to be 4 to that obnoxious power y plus 4 over 2, and then minus 1 equals x. And I know it seems kind of obnoxious to do all this work, but it's going to be a lot easier to just plug in y values and then evaluate that expression than it would be to plug in x values and just hope that they work in this log expression. Alright, so we'll come back to this in a second. The vertical asymptote is normally x equals 0, but this thing has been moved. It says x plus 1, and the plus 1 moves it left 1, so this would be x equals -1. And it hasn't been reflected horizontally, so it's still branching off to the right, so the domain would be all the x values that are greater than this -1 here. The x-intercept is whatever you get when you plug 0 in for y, and that's actually really easy to do with this thing here. Because 0 plus 4 is just 4, 4 divided by 2 is 2, and 4 to the second power is 16, so 16 minus 1 is 15. So that's considerably off this graph. We're not going to see that, but we can also look for the y-intercept. That would be where 0 is the x value, and I'm going to try plugging that in up here. So 0 plus 1 is just 1. And if you were just evaluating this log term, that would be like saying 4 to what power equals 1. And anything to the 0 power equals 1. So this whole thing would just evaluate to be a big ol' 0. 2 times 0 is 0. And then minus 4 is negative 4. So this thing should cross at negative 4 here. So at this point, after graphing that vertical asymptote, I know I could just make an xy table, plug in a couple y values, and see what happens. So I'm going to try to pick a couple y values that would work well when I plug them in. Like if I plug negative 3 in here, negative 3 plus 4 is 1, but then I'd have the 1/2 power. Actually, that's not too bad. So that would be like 4 to the 1/2 power minus 1. And a 1/2 power is a square root. So the square root of 4, which is 2, 2 minus 1 is just 1. So when I plugged in negative 3, I got an x value of 1. And if I tried like negative 2 next, negative 2 plus 4 is 2. 2 over 2 is 1, so 4 to the first power is 4, minus 1 is 3. And at this point I can pretty much see what this graph is going to do. It's branching off to the right, and as it goes to the left, it's just approaching this vertical asymptote.